Hello everyone, I'm Ouyang. Today we are going to present our work leveraging historical medical records as a proxy via multimodal modeling and visualization to enrich medical diagnostic learning. This work is a collaboration with Zhongshan Hospital of Fudan University. First, let me introduce the background. We know that medical simulation technology is a very common method in medicine. Early medical simulation was mainly used for physiological research to help doctors and medical researchers better understand the occurrence and development mechanisms of disease. Now, medical simulation technology has been widely used in the field of medical education. Simulation-based medical education (SBME) is an education method that uses tools to simulate clinical scenarios. It plays an indispensable role in medical training. Through repeated practice and simulation, learners can gradually improve their diagnostic abilities. Nonetheless, SBME evaluations are often immediate and aim to enhance learners' medical skills and practical expertise, rather than to enhance the summative medical diagnosis that emerges from time and experience. Interns may tend to overlook or rely on certain modalities due to their lack of mindset and clinical experience. Existing works primarily focus on adapting state-of-the-art techniques to improve model performance, but overlook the impact of individual modalities on the contribution to model results. To address these issues, we conducted this work. We shadow and gain insight into the mental apprehension processes between experiment physicians and interns. We facilitate and enhance the learner experience of interns physicians by developing a visual analysis system embedded with a multimodal model. We demonstrate the validity and the reliability of our approach through 2 case studies and expert interviews. To gain a deeper understanding of customer procedures within the medical diagnostic process, as well as the learner experience of interns, we collaborate with a team of 5 domain experts from a local hospital. Following interviews with all experts, we combined a list of requirements to improve the medical diagnostic learning experience for interns by addressing some concerns. Our system is intended to be consistent with the learner cycle principles, allowing users to achieve their learning objectives, enhance their self-awareness, and engage in self-adjustment. Here is our system's architecture. The processing of medical data in different forms is conducted by the backend engine. It uses a multimodal model to make predictions and employs interpretability techniques to explain them. The front-end visualization facilitates interactive exploration for improved diagnostic learning. Next is the backend part. We use the real-life clinical dataset for diagnosing cervical spine disorders. The dataset comprises 750 patient records collected during hospital visits for cervical spine discomfort. Each patient has a unique card ID that corresponds to a set of clinical records, including demographic information, laboratory test results, MRI images, clinical reports, and diagnostic findings. We organize this data into 3 modalities, namely the indicator modality, text modality, and image modality. Especially, the design of our model revolves around the classification of patients into 3 distinct categories. The category information is extracted from the diagnostic findings. We conducted experiments on each modality, integrating their performance and interpretability. We select XGBoost for indicator data, Clinical BERT for text data, and CovenX for image data. For post-hoc interpretability techniques, we select SHAP, attention weight, and grade CM. Next is the front-end part, which consists of 4 parts. I will introduce them one by one. The user panel offers users an overview of the multimodal medical dataset and the model performance, while also providing descriptive statistics about the dataset, data quality, and sources for each modality. Embedding transition wheel connects the fusion model embedding and the 3 modality data, indicators, text, images, embedding spaces. Each patient is represented by a node, and the connections between each projection allow users to trace the same group of patients across different embeddings. This is modality exploration view. As each modality possesses its distinct characteristics, we propose visual interfaces and interaction for each modality individually to present intuitive representations. Here, I mainly introduce the indicator modality. Based on the physician's suggestions, we extract 34 indicators. These indicators are stacked in a collapsed table, where each row corresponds to an indicator. In the mode, each row includes the indicator name and approximate distribution of indicators concerning the last of the patient groups, the mean value, thereby enable the user to gain an overview of the indicator modality. The overall distribution of indicator data is exhibited using strip charts. The details can be viewed by calculating and expanding each feature, reviewing a baseline plot, illustrating the data value of each instance. Moreover, a bar chart is employed to exhibit the Shapley value. The table supports operations like sorting by contribution and filtering by indicators, providing clinicals with more control in the exploration. It is worth noting that our three modality views are interconnected. When the user selects a patient, the views of other modality will also update accordingly. We have evaluated 4 types of visualizations, namely histogram, density plot, volume plot, and bin-swarm plot. It was observed that density and volume plots are suitable for representing continuous data, but inadequate for discrete data. In contrast, histograms employ interval grouping and frequency counting to facilitate the visualization of data distribution. However, when it comes to depicting data density and clustering, bin-swarm plots have exhibit distinct advantages over histograms. Bin-swarm plots have been found to offer a more quality and efficient representation of the indicator distribution. The embedding transition wheel and modality exploration will assist users in identifying and comparing different patient cohorts across modalities. The comparison wheel facilitates a more detailed analysis of patient-specific similarities and differences. Through this wheel, users can perform a more fine-grained comparison of individual patients, considering both aggregate multimodal data and detailed modality fusion. The process of decision fusion for the selected patients is represented using hybrid visualizations. On the left side, 3 groups of horizontal bars illustrate the predict probability of the selected patient for each of the 3 modalities, listed from top to bottom. On the right side, a separate group of bars displays the final prediction after decision fusion has appeared. Each bar in a group corresponds to a diagnostic entry within the dataset. The center pie chart provides a visual representation of the percentage contribution of each modality to the fusion probability at the item level. Links connect the bars of corresponding entrants in each group, while the pie and links are colored to match their source modality. Facilitate the identification of modern correspondences. Initially, the Sankey diagram design was explored as a means of visualizing the decision fusion process. However, it was discovered that this design did not actually align with the multimodal fusion task at hand. Linking individual modality bins and final probability bins using Sankey links would have resulted in visual clutter. Therefore, experts were consulted, and it was decided that a more intuitive and easier to interpret display of the fusion results could be achieved through the use of simple bar charts and pie charts. Next is a simple demo presentation of the system. We can see that the interaction is very direct and easy to understand. Next, I will introduce the evaluation, which is divided into 2 parts, case study and expert interview. 2 case studies. Case 1 focused on experiment physicians, demonstrating how our system addressed their concerns and meet their requirements. Case 2 explored whether our system improved the learning experience of interns in medical scenarios. Before conducting these case studies, we organized a tutorial session with the expert involved. They were introduced to the visualization designs, interactions, and workflow of our system. After a brief familiarity period of 10 minutes, the experts engaged in 1-hour case studies while sharing their thoughts in a think-aloud manner. We then conducted interviews to gather their feedback on our approach. All experts acknowledged the effectiveness of our system in enhancing the medical diagnosis learning experience, and they can independently explore multimodal data. In general, all experts confirmed that the visual representations were intuitive and the system was easy to use. In addition, the experts also made some suggestions, hoping that the system can further help improve the data quality and add some interactive tools to detect any missing or incorrect information. Our approach utilizes various post-hoc interpretability methods for multimodal models to help users understand model predictions and facilitate learning. However, it is important to note that the explanations provided by the model may not always be accurate, which could lead to incorrect decision-making. Hence, we caution against directly relying on the system for high-stakes clinical decisions. Moreover, our future plans involve incorporating additional types of data, including temporal sequences. Further, considering the improvement of communication between interns and our system, a potential need arises for personalization in human-AI interaction. Thank you for your attention.